Okay, let's talk about image quality and QA. And I would say, I know for sure the X-ray students are going to be in digital imaging. I can't remember if this radiation therapy cohort is going to be in digital imaging. But regardless, when we talk about image quality, I'll be talking about it from a standpoint of digital imaging. And there's some really important stuff in here. In this chapter 6 especially, when we talk about image quality, there's some very specific ways that we need to talk about it. Because if you think about it, and I'm sure I've said this in some form before, but we are probably the most creative people in medicine. We're among the most creative people in medicine. Like in general, nursing, there's not a lot of painters who run off and want to become nurses, right? You find a few rare exceptions to that rule. Like I think about Walt Whitman. He was a poet who was also a nurse. He cared for the infirm during the Civil War. So there's a few exceptions, but on the whole, people who are super creative types don't run off and want to become nurses. Why is that? Well, nurses are not super creative, if we're honest, right? They have to go by the numbers. They say, okay, if I give X amount of this medicine at this time, then this happens, period. Nothing creative, nothing fancy about it, right? But for us in X-ray or nuclear medicine or radiation therapy even, we are creating something. We're making a picture, right? Or we're making a treatment plan, or we are creating a set of images that can be used to model all sorts of things. CT is a very creative field, and so when we talk about image quality, we're talking about a creative thing. We're talking about quality the same way that a photographer talks about quality. We're going to talk about contrast and detail, and we're going to talk about tones and shades of gray, and all these things that are very artistic, right? But the reality is that we can't just content ourselves with an artistic discussion of it, although that's important, and each one of you right now is an artist developing a style as an X-ray tech or as a therapist or as a radiographer. You're developing your personal style, right? But at the same time, we have to find some hard science that can measure quality. And so I'm not going to spend a lot of time talking about the creative part of it. Unfortunately, that's what one of my areas of interest and expertise. I have a master's of fine arts and creative writing, so I can talk about creativity all day long. I love thinking about creative process. But when we talk about CT quality, while there is definitely a stylistic part, and I want to definitely encourage you to explore that as you're out there in the clinical field and you're thinking about things creatively and you're creating new responses to situations, we also need to understand that there's a science to this, and that science can help us better understand quality. So, well, there were supposed to be objectives there. I'm sorry, I don't know where the heck they went. But what we're largely going to be talking about is scan parameters, okay? How we set up these images and the way that we measure them. We'll talk about specifically, we'll get at some depth about spatial resolution and contrast resolution. We'll track pretty closely with the textbook on those. I'll very briefly touch on temporal resolution, and then we'll jump into quality assurance, and we'll look very specifically at artifacts. So sorry, I don't know what happened to that last slide, but those are my objectives for us with this presentation. So with these scan parameters, these are covered at some depth in the first few pages of chapter 6. And some of these we've already hit on pretty well, like the milliampere and time in seconds, which is what we multiply together to make the term mass. So this milliampere time is how we largely control density of the images, or how intense the quantity of X-ray photons is that's being produced. So in that regard, it's directly tied to patient dose. And when we're using filtered back projection, it's also directly tied to image quality. So for filtered back projection, we've already talked about how quality basically is quantity, right? That if we want a high quality image with low noise, we have to give the patient quite a bit of radiation, quite a big dose, right? And so one of the very first things that I think it's important for us to talk about, when she mentions scan parameters on the top of page 58, she says, among the factors that operators control are milliampere level, second time, slice thickness, field of view, construction algorithm, and kilovoltage peak, as well as pitch. All of these scan parameters, when we think about them as CT techs, we're asking what will form an optimal image. That's a very important term, the optimal image, right? When I think about optimal image, this is an image that balances both patient dose and these parameters, right? So it may not be the prettiest picture that I've ever seen, but it's been acquired in a way that has balanced both the dose and its diagnostic value. So optimal images will balance patient dose and diagnostic value. Okay, so that being said, milliampere is, for X-ray techs, a big part of where dose comes from. But in the world of CT, we've also said that KVP is directly tied to patient dose. So as KVP increases in the world of CT, dose increases also. That's one of the main ways it breaks with traditional X-ray. That it does have a connection between KVP and dose, and that has to do with the way that filtration works and also the way that the computer works. Okay, the field of view, the scan field of view, not the DFOV, but the SFOV, is going to be something that we have control over, and we can determine what the scan field of view is, and that can be tied to both the image quality, how much resolution is in this image, as well as the areas that have been exposed in the patient. And that is on page 60 in our textbook, the discussion of scan field of view. So you can see this discussion of optimization. If you're wondering where is that in the textbook, it's page 60, box 6.4. She says the appropriate selection of mass and KVP is critical to optimize radiation dose. That's not just an empty word. It's a very specific term. And so I would want to make sure that we understand that. Another thing that she talks about is this uncoupling effect. And that is precisely what we're hinting at when we talk about how KVP, for the CT point of view, increases patient dose. This uncoupling effect is anytime I start rattling off a bunch of scan parameters, people's eyes start to glaze over and they're like, whatever, right? This is a lot of scientific mumbo jumbo. That is precisely what the uncoupling effect is. And it's directly tied to, so I would say that's a sociological phenomena, right? The machine doesn't sit there and say, I'm so uncoupled, I don't know what these scan parameters are, right? No, technologists get uncoupled from an understanding of this stuff and its impacts, and then all of a sudden the scanner has been incorrectly, created, right? We'll look at some great examples of that this summer. One of the big ones that pops immediately to my mind is the case of Raven Knickerbocker. Has anyone ever heard? It's a real name, by the way. Raven Knickerbocker. She's probably the most infamous CT tech of all, right? She's like the, I'm trying to think of historical bad guys. She's like the Dr. Doom of CT techs, right? Crazy and kind of weird. She over-irradiated a kid probably 200 times what he needed for a CT scan. It's really unclear what exactly happened in the scan room, but the kid received radiation burns on his head from her trying to do a CT of his head. So they actually did. This was right at the advent of them being able to determine what kind of damage was being done at the cellular level from CT scans, which was about 2008, 2009, I think. I could be wrong. But they sent off a blood sample, and she had actually caused irreparable damage to like T-cell lymphocytes and stuff like that, possibly skin cells, right? So that uncoupling effect is a real thing, right? And one of the ways that we think about it, especially in X-ray, is dose creep. So this is another sociological effect where we no longer understand what the technology is doing, and we now are over-irradiating the patients a lot. Because we simply don't understand scan parameters or dose parameters or whatever. We can still get pretty pictures. So that's the thing about CT, right? I can get you beautiful pictures and over-irradiate patients all day long. I could train a monkey to be that kind of CT tech. Literally train a monkey to be that CT tech. But if I want an optimal image, that requires some thought. So that is why I'm rattling off all this stuff, and I want you to be aware of that sociological phenomena. An important part of this is why I spent so much time talking about pitch and slice thickness. So if I've set up my KVP and my MA appropriately, I can still over-irradiate the patient by not having an appropriate pitch, right? Or where it's a balancing act, I could have my parameters set up right, but because the pitch is off, still get crappy pictures, right? So I need to be choosing the right parameter and the right amount for every exam I do. Now, fortunately, there's been a lot of science already done on this, and we have a pretty good idea of what, in general, these parameters should be. And we'll spend a lot of time this summer. If this seems really vague, what I'm talking about right now, believe me, you will become intimately aware of what the general scan parameters should be for almost every single exam that you could do this summer. So this is just getting us in that direction. Automatic tube current modulation is like the CT text version of automatic exposure control. They are different, but they do a very similar thing. In automatic tube current modulation, the scanner is able to modulate the amount of MA that it's giving based on the thickness of the anatomy. So based on the attenuation values of the anatomy, the CT scanner will change the MA settings accordingly. So if it has a thick part that it's scanning through, it's going to bump up the MA. If it has a thin part that it's scanning through, it's going to drop it down. And she says that these automatic exposure control techniques can cause anywhere from 15 to 40% reductions in dose. Now, that's with a little caveat, right? I was thinking about it this morning as I was driving to work. Some of us drive Japanese-made cars, and some of us drive cars that were made in Detroit, and some of us drive cars that were made like in Germany, right? Things like that. What's interesting is for each one of those nations, right? Japan, the U.S., and Germany, there are CT scanners too, right? And they're about the same kind of thing. Like the Japanese CT scanner, it's going to run a long time, won't cause you a lot of problems, but some things are going to be kind of different about it, right? The GE, the American-made CT scanner, it's going to be pretty much everywhere you go, right, to where you almost can ignore that it exists. It's going to be very simple to use, just like a Dodge is very easy to drive, right? And it's going to be a workhorse. Versus these German CT scanners like Siemens or Philips, which comes from Great Britain, these imports, they're going to be the fancy ones. Like these are the Mercedes-Benzes of CT scanners, right? The reason I'm pointing that out when I talk about automatic tube current modulation is this is one of those really weird things that CT scanners can do, and each one of them do it differently. That's the unfortunate truth. Each one of them does it differently. Why is that such a big deal? Well, let's think about shielding. Has anyone ever seen the techs apply bismuth shielding to a patient prior to CT scanning or with CT scanning? They might put a breast shield on the patient. Depending on if you're operating a machine from Germany, Japan, or US, that can or cannot reduce patient dose. So what the heck am I talking about? This automatic tube current modulation thing, if it sees that shielding there on the scout image, it's going to think, oh, I got to get through all that shielding too. And just crank the dose up that much more in order to get through the shielding. The robot did that. Like the robot made that decision. So I need to know how it's applying automatic tube current modulation. Is it doing it, basically the question is this, is it doing it based on the scout image, or is it doing it based on like live scanning, what it's actually getting as it scans? Because if it's doing it off the scout image, I do not need to put that bismuth shield on the patient until after the scout image. I need to get up off my lazy butt and put the bismuth shielding on the patient after I've done the scout. Now I've told CT techs that, and I've read it in the literature, but do they do it? No. So is that reducing patient dose? No. So you need to know what kind of car you're driving. If you're driving the German car, can you throw the bismuth shielding on? Yes, you can, because the German car is smart, right? You can drive it like a moron and go 200 miles an hour and no one's going to get hurt, right? You try to do that in the Dodge, someone's going to get hurt. All right, enough with putting down Detroit. I actually really like Detroit cars. Reconstruction algorithms, like we've already talked about, what kind of reconstruction we're doing can be tied to the quality of image that we get and as well as patient dose. So the big takeaway is here, like I've already said, the filtered back projection, FBP, filtered back projection reconstruction, patient dose is directly tied to image quality. So if I up the dose, I will get better pictures. I will get less noise. With iterative reconstruction, and this is exactly the reconstruction process that we stole from nuclear medicine, right? Y'all had it first, and we said, hey, that's cool and shiny. We want that too. So they brought that into CT scanners. Now that we have this iterative reconstruction, that's no longer the case. So we can reduce patient dose while still getting good, high-quality images. Okay? So that's all you really need to know about each one of these, that each one of them is a balancing act. So we've talked quite a bit about quality. We might as well go ahead and define it now. And I've said that we're not going to use an artistic definition. We're going to talk about two main areas, that is spatial resolution and contrast resolution. Each one of these can be measured. And so we'll talk more about how to measure them here in just a minute. Box 6.6 on page 61 has a little bit more depth on that. So let's talk about spatial resolution. And this is the part where if you're starting to fall asleep, you should probably wake up. Because if you look at my pages 62 through 63 in my textbook, they've got stars and bars and all sorts of things all over them. Because this doesn't just relate to CT, this relates to digital radiography, this relates to portal imaging, this even relates to some degree to nuclear medicine stuff. This discussion of spatial resolution is one of the best ones that I've ever found. And what she says is, we can directly measure spatial resolution by looking at line pairs. And one of the things that I've got highlighted in stars all over it right here is where she says a line pair is not a set of two lines, but rather a line and the space between the lines. So this is conventional definition. So if I think that a line pair is those two lines, I will never know what my spatial resolution is. It is always the line and the space. That's the line pair. So when I'm counting line pairs and things like that, and I'm measuring them in line pairs per centimeter or line pairs per millimeter or whatever resolution I'm working with, I need to always be mindful of that. I like how simple she makes that. That is a direct measurement of spatial resolution. So I can also theoretically now chart that out. And this may be another place where people's eyes glaze over, but this modulation transfer function is super important. It's super important. And so understanding what it is important to top of page 63. Again, I've got stars and everything. The MTF is a ratio of the accuracy of the image compared with the actual object scanned. Therefore, MTF indicates image fidelity. The MTF scale is from 0 to 1. The MTF scale is from 0 to 1. So a 1 means it's complete fidelity. Whatever the size of the object is, that's the image size, right? As this thing starts to, and these things always slope down like this, right? The MTF function always is going to slope down. What it's sloping down from is as that object size shrinks. As the objects are getting smaller and smaller and smaller, like these stupid apples that she's got, this is not as helpful of a thing. I don't think apples are stupid. I love apples. But these little tiny apples are going to have like a 0.5 in terms of MTF. Versus the big apple, New York, is going to have a 1, right? That's all she's trying to point to, is that as the object size shrinks, we would expect the MTF to decrease as well. The degree to which it decreases is what we're measuring. So that's one of the ways that we'll determine, is this a good image, is this a high quality image? We can chart this out. We do measurements, we do these measurements sometimes monthly, sometimes daily, depending on your facility, and we chart this out. Is it still accurately capturing the object size? So she goes on to say MTF graphs depict spatial frequency along the x-axis and MTF along the y-axis. And as expected, the graph shows that as the size of the object increases, MTF also increases. The inverse is also true. As the size of the object decreases, the MTF decreases. What we're interested in is the degree to which it decreases for each system, right? So if I'm driving the German CT scanner, the Siemens, I would expect that MTF to fall off a little bit slower versus maybe one of these Japanese CT scanners like the Toshiba or the Hitachi. I would see that MTF fall off quicker. It's going to have less spatial resolution, right? And that's a measurable thing. And I think one other add-on to that is that we're not just talking about this along the X and Y axis. We can also talk about longitudinal resolution. So this has to do with slice thickness. And trying to find exactly where she talks about longitudinal in-plane versus longitudinal resolution is top of page 64. This is the resolution along the z-axis direction, right? So this is those problems that we have where maybe more than one thing has been sampled in this area. How does the machine resolve that? And we are going to do some activities around this material so that we understand both how to talk about it and become fluent in there, but also maybe understand a little bit of the mathematics for how this plays out. So here are the factors that affect spatial resolution, and us all being kind of hands-on people, I wanted to show you these images. You can definitely see it here in these temporal bones. One of these has more spatial resolution than the other, and that is going to be dependent on the matrix size. So the larger the matrix, the smaller the pixels will be. The display field of view is going to have an impact. Pixel size, like I just alluded to. The pitch and the slice thickness will have impacts on this longitudinal resolution. And then these reconstruction algorithms. Can we get rid of noise? Focal spot size and patient motion are kind of givens. We don't normally mess with those too much, but the scanner can make the determination about focal spot size. For patient motion, it's best just to tell the patients to hold still. All right. The other way that we can talk about quality is going to be contrast resolution. These are the big two, is spatial and contrast. And we might also call this low contrast detectability or even system sensitivity. So when we talk about how sensitive CT is, its sensitivity levels, we're talking about its contrast resolution. When we're talking about its contrast resolution, we're talking about its ability to differentiate between two objects having close to the same attenuation value. Two objects having close to the same attenuation values. So we will look at things like the liver, or we will have a phantom that imitates the liver, and that's how we'll measure this contrast resolution. And CT images, the objects can have like a 0.5% contrast variation. We can still distinguish that. So it is, across the board, one of the most sensitive exams that we can do for low contrast resolution. The only thing that has it beat sometimes is MRI in terms of anatomic contrast. Yeah, I think that's all I need to say about it. These slides are also in the textbook, and they show the difference. It's on page 69. They show when we window and level differently, we can see that there's clearly something going on in the liver there. Again, the factors that affect it are going to be similar to spatial resolution, but a little bit different. We have mass and patient dose, the pixel size, and what's interesting about contrast resolution, as the pixel size increases, we're actually able to determine contrast a little bit better. So spatial resolution likes a small pixel. Contrast resolution sometimes likes a slightly larger pixel. She talks about that just a little bit. The slice thickness, and then that reconstruction algorithm, as well as patient size. And one of the things that she points out, bottom of page 69, is how to look at these low contrast objects. And this is helpful to all of us if we're ever windowing and leveling and we're trying to look at, for example, something in the liver or in the brain. What we need to do is for low contrast objects to be visible, the window level must be set near the average density of the object, and then a small window width will be used so that only like small groups of things around it can be made visible. So we'll window level to the level of the object, and then we'll make a decreased width so that we can see it very clearly, so that it kind of pops. One other thing that, well, I guess that's all I need to say about that, because we'll pick up the other points here on noise. Noise has a huge impact on low contrast resolution. Okay, so I can still have okay spatial resolution if it's a noisy image, but I may not have the low contrast resolution that I need. And like I said, we've tied the contrast resolution directly to sensitivity. So if I've got a noisy image, I've also got a less sensitive, a less diagnostic exam. Not because it's spatially bad, but because the contrast is off. And so the way that we will largely measure noise will be a signal-to-noise ratio. And a high signal-to-noise ratio is good because it's saying that you have a lot of signal and just a little bit of noise. So again, that's a high SNR, signal-to-noise ratio. And she points that out kind of bottom of the first column on page 68. She says that in CT, the number of X-ray photons detected per pixel is also referred to as the signal-to-noise ratio. Another important thing to be able to think about here is the standard deviation, which we introduced when we talked about ROIs, because this is how we're going to measure the noise in an image. This is an image of a water phantom, and so I'm looking forward just a little bit towards Chapter 7 when we talk about quality assurance in CT. But what we do is we scan phantoms, and then we place ROIs on those phantoms, and we measure things like a standard deviation. So she talks about how the standard deviation measurement is indicative of the amount of variance, right? So the way that we would work with this image here is I would draw a circle, an ROI circle. I'll draw that a little bit more dark here. I'll draw an ROI circle maybe at the center of this water phantom. This is all water, right? But I've got this rippling ring artifact here, and so I would expect to see some standard deviation there. Whatever that standard deviation is a pretty good indicator of the amount of noise in this image, because the reality is this is just water. There shouldn't be any ripple in it, right? Okay, and finally, temporal resolution. This has largely fallen by the wayside because we've got scanners that scan very fast now. But back in the day when we were still scanning on single row scanners and things like that, we had to think a little bit about how rapidly the data could be acquired. This is more of a historical discussion now than anything. But it is helpful to know that temporal, it's not talking about the temporal bone, it's talking about time. It's talking about how quickly can the machine move. So here's a quick review question. Let me get this stuff out of the way. So the appropriate technique for a given patient exam is 200 mass. The technologist mistakenly uses 100 mass. Which aspect of image quality would be most affected? As we think about it, it's going to be contrast resolution, okay? Because we said that as we drop the patient dose, we will see an increase in noise, and so that sensitivity of the image will be off. Okay, so let's talk a little bit about QA. So I'm switching gears now. I'm moving on to Chapter 7. And what we do is every day, in most any department, they'll warm up the CT. They'll go through about a 10-minute warm-up routine, and they're going to throw a phantom inside the gantry. So just like a water-type phantom that has some different stuff inside. There's a picture of what different phantoms look like on page 72. This is a CT phantom. So when I say phantom, I mean this QA phantom. Now she alludes to the fact that you can also have body phantoms. You can have phantoms that look like parts of the body, and those are designed to have ion chambers inserted into them so I can replicate patient dose patterns. with the body phantom. But this QA phantom, and this is actually the one that's approved by the American College of Radiography. So if you're working at an ACR accredited CT site, they have this phantom and they go through the ACR QA stuff, right? Otherwise, they might just use whatever the manufacturer of the CT scanner indicated, right? So for me, I've never actually worked with an ACR phantom. I've always just worked with GE phantoms or Siemens phantoms or whatever. But we're going to, after the warm-up, we're going to throw the phantom on the machine and just scan the phantom. And then we do a series of ROI measurements, or even sometimes distance measurements on the phantom, and determine how well is the image replicate what I know is inside the phantom. Because I know exactly what's inside this phantom. I know the density of each object in it. I know the size of each object in it. So I can directly measure image quality because I know everything that can be known about the phantom. And I'm not exposing anyone to any kind of radiation. So phantoms will definitely, they're definitely a way that we will move CT into the future, right? As we come out with better ways to scan and better ways to reduce patient dose, we're not going to do those experiments on people. Right? We're going to do all those experiments on phantoms. So this is one area that, like, when it comes to things like 3D printing, you know, we will immediately, when we've already started developing 3D printers that are printing CT phantoms so that we can better understand what the CT scanner is doing. Basically, the responsibility of any QA program is shared between the CT technologist and the medical physicist. So it's our responsibility to do the daily scans of the phantom, and then the medical physicist will come in and create like the MTF table or a measurement of patient dose based on how the scanner is operating. There's some basic rules to the any QA program, and she's got them on the top of page 71. And these tests, they need to be performed on a regular basis. So whatever your departments, whatever you've worked out with the physicist, whether that's daily or weekly or whatever, they need to be done every day that they're due. And the results from all the tests must be recorded in a consistent format. In fact, every facility I've ever worked at uses the exact same form to record their data from this. And the documentation needs to indicate whether the test parameters within the specified guidelines. So here's just another example of a QA phantom. This is actually the one used for spatial resolution. And so if I'm going to zoom in on this picture, I've got line pairs here, right? And it's almost like an optic test. The machine, I can actually throw an ROI on these line pairs, and I would expect there to be a certain standard deviation within those line pairs. If I get something other than that measured standard deviation, then I can say image quality is off at this line pair level. So I can say very specifically how sensitive this scanner is to like small spatial resolution objects. So here is these QA phantoms, and we measure all sorts of things on them. I put a little star out there by radiation dose because, again, we typically don't measure dose just off of this QA phantom. We will measure it with some kind of body phantom that simulates a patient's body. We'll place an ion chamber inside of it and scan it. We've just got 3 more slides and we'll take a break. So here's a discussion of artifacts. Anything appears on the image that's not in the object, we're going to call that an artifact. Okay? They can have a bunch of different ways that they look, and they're broadly classified as either physics-based, patient-based, or equipment-induced. Okay? And she goes into quite a bit of detail about that. I would review that discussion of whether they're physics-based or patient-based or equipment-induced. It is, let me see where it's at, I believe top of page 75. I'm not as interested in whether a particular artifact is like physics induced, because a lot of times they bleed into each other. Like there's some physics here, there's also some equipment issues that are going on. They all kind of have some overlap. But let's look at the specific artifacts we're talking about. So here are a number of different artifacts, and this is what we're going to be doing a Kahoot on in a minute. This shouldn't say Ren, it should say ring artifact. And so this is the water phantom. These rings do not exist inside the phantom. The scanner needs to be recalibrated in order to get rid of this artifact. And she's actually pretty good about telling us what causes the artifacts and then how to get rid of it. So this one requires some recalibration. If it continues after that, it may be a detector element or something. This is an out-of-field artifact. This is the exact same patient, the exact same level. The only difference between these two images is the patient's arms are down. So this is why we bring a patient's arms up, because the arms are creating this beam hardening artifact that's streaking the heck out of the liver and giving us a really crappy image. Right? So the way that this is out of field, anytime we see this, we just need to have the patient's arms up. It could also be caused by poorly centering the scanner. And then let me zoom down here. This is a beam hardening artifact. I'm going to zoom in just a little bit more. We can see these lines or these streaks through the image. They're almost on every CT skull at the level of the temporal bones, because this is a super thick bone. And all of a sudden, it's like the Klondike bar, right? We go from this super thick bone to ice cream in the center, right? That's how your brain is. And so when the beam is hardened or attenuated by all that bone, and then it hits that ice cream, it hits your brain, it thinks that it doesn't know what to do with that, right? When the scanner's reading that, it has struggles with that. So we're going to see streaks at the level of the temporal bone. We'll call that beam hardening. And she says that there's two basic beam hardening artifacts, and this is the only discussion I found of this artifact anywhere, right? And it's actually on the boards. But a cupping artifact is when we have beam hardening that causes the periphery of the image to be lighter. Why it's called a cupping artifact, any other discussion of it, I've never found. But it's literally a board registry test item. Cupping artifact, this is the only discussion I've ever found of it. It's an artifact, beam hardening artifact, that causes the periphery of the image to appear lighter. Typically what we're talking about are these dark streaks or bands. Let's move along. This is a windmill artifact, and it's related to not having an appropriate pitch. So if we have a pitch that's eclipsing what we can scan, then we get this weird windmill artifact. Most scanners have stuff already built into them that allows us to avoid this artifact. So it's a pretty rare artifact to find. And then finally, this is probably the most subtle one to see, but the one that I would look at most closely, she talks about edge gradient effect. On the bottom of page 76, the edge gradient effect. What happens here is if I've got barium in the patient's stomach and then just regular old liver in the patient's liver, the machine gets confused. It doesn't know where the barium stops and the liver begins. So I get some barium in the liver and some liver in the stomach. The machine just flip-flops them. And that flip-flopping process it calls a gradient. Now, typically when I think about gradients, I think about the old trapper keepers. You know those things that have like unicorns on them and they're flying over an island or something? There's always a gradient in those images. Or conversely, Pink Floyd's Dark Side of the Moon, right? The rainbow. A rainbow is a gradient. It's colors moving from like yellow down to purple or something, right? So a gradient is any time that colors move from one color to another in a smooth process. We see gradients all the time. This gradient's hard to see, but if I zoom in here, I can see here's the gradient direction of the barium here moving into liver here, right? Or the air here moving into liver here. So I've got this kind of shading effect that's occurring. That's not really there. There's no barium in anyone's liver, thank God. But the machine thinks that possibly there is. All right, and that's it. This is a CT image of a monk. Not a real monk. It's a statue of a monk. But I think they found dude's skull inside this thing, if I remember right.